Alright, so we're going to start with number 3 here, since that was asked for, where we have an extension cord made of 2 wires, and this length, and it's connected to an electrocutor which draws this much current on this line. How much power is dissipated in the cord? Alright, well, this one actually harkens back to an example problem we did after talking about voltage, current, and resistance, like back before we started the big packet. In that, this is number 3, the resistance of the cord depends on its physical characteristics. Things like the material, the length, and the diameter, and the shape. So those physical characteristics are what are going to determine the resistance in the cord. Then I'd probably also make sure I showed in here that I understood that power is the rate energy is used, right? And also it'd be good to show that I understand that current is the rate charges pass through. I used to always use the term charges move, but I think pass through is a better term than move. We're not talking about the velocity of the charges, but the rate that they move past a point. All right, so that would be a good why. I'm showing that I understand about the resistance of the cord and that what power and what current are, because I'm going to use those facts from my equation sheet. Power-wise, let's see, here it is. I'm going to use, I have my power equation over here where power is related to the current and the voltage, the resistance, the current and the resistance, and the voltage and the resistance. So I kind of can pick whatever form of that makes the most sense to me. And then I have my equation here for resistance, which is based on the physical characteristics, the resistivity, the length, and that cross-sectional area that we did before, right? All right, so I'm going to actually use both of those. Let's see, put down, I'm going to use that R is the resistivity, length over area. And I just want to look at the problem. And I'm going to use that E equals I squared R. Alright. Hold on 1 second. Alright, so, let's see. Let's look at the specifics here now. We've got, it has that diameter, and it's copper. So its diameter, better put that in meters, right? Yep, so I'm going to draw myself a little picture just so I can picture it better. They're saying that this is 0.129 centimeters. Is that right? Did I read that right? Okay, and it's copper. And the reason it's important that they tell me that it's copper is because I need to use the back of my rubric sheet and find the resistivity for copper, which is down here. Be careful, this is density. Kilograms per meter squared, you don't need that. You need the resistivity of copper, which is this value right here, 1.68 times 10 to the minus 8th. So, for copper, it's 1.68 times 10 to the minus 8 ohm meters. All right, so I'm going to figure out the well, combining these two equations. Power is I squared R, and for the R, I'm going to put in this. So I'm left with power is I squared times the resistivity, length over cross-sectional area. The one assumption I have to make about this wire is that the cross-sectional area is a circle, right? So that area is going to be pi r squared, right? The length, so that's the one a lot of people would first make a mistake on. Circuit has two wires of this diameter and this length. So the length isn't 2.7 meters, but the length of both those wires combined, which would be 5.4 meters. All right? So, and that might even be something I put in my how, but in my why. So let's see. So I'm going to start putting in my values. Power, I, they tell me, I think, 14 amps for me. Squared. My resistivity, 1.68 times 10 to the 8th ohm meters. My length is 2 times 2.7. It is. Thank you very much for that. I would have really messed it up. Over my cross-sectional area, which is pi times r squared. Here's my diameter, right? So my radius here would be 0.0645 centimeters, which is 6.45 times 10 to the negative 2 centimeters. Sorry, I'm kind of jamming things in here. Which would be 6.45 times 10 to the minus 4th meters. Square here. That's a pi. Yeah, I'm going to rewrite this nice and big here. So rewriting this, since I got all jammed up there, it's 14.0 amps squared times 1.68 times 10 to the negative 8 ohm meters, all multiplied by 2 times 2.7 meters over pi times 6.45 times 10 to the minus 4 meters squared. Yeah, that'll do it. Should come out, right? Let me check. Pull out my calculator. Let's see, 14 squared times 1.68 to the EE negative 8 times 2 times 2.7 divided by, parentheses, pi times 6.45 e to the negative 4th squared, close parentheses, 13.6. I wonder if that's right. All right, so we're going to do number 11 here, which is good because 11 is a full circuit problem where for my y I need to do the diagram and the plot and everything else. So I'm glad we're getting a chance to do one of these today. I'm going to grab the diagram just so I don't have to flip back and forth. minimize that. So there's my diagram. I'm going to actually take the time to redraw this so that you have a better idea of what I expect. Except yours will be neater than mine because I'm drawing on the board, which is harder to do than drawing on paper and pencil. Yeah. We'll see, Gifty. We'll see how yours is. Did you just ask Joe if he solved yours for you? Oh. I thought you said to get mine. I'm actually going to change the drawing of this a little bit because the way this is drawn, it's a little deceptive. I'm going to do one thing differently. I'm going to connect all three of those, and then I'm going to connect them up here. It doesn't change the electrical arrangement of it, but I think it'll end up making it easier for you guys to understand. And now I need my values. Let's see. 12 volts. R1 is 3.9 ohms. R2, 7.8. R3, 19.5 ohms, and R4, 11.7. All right, so there, besides a couple places where I ran over, like here, that's a pretty passable circuit diagram. Ideally, all my resistors would be the same size and things like that, but in general, that's okay. Now I'm going to do my plot. Well, I would do my currents first. How many currents? Well, one question right off the bat. How many junctions? 2. And that's one reason I kind of changed my diagram, because if you look at the one the book gave you, it looks like there's many junctions there. And you can really, there's really only needs to be 2. So I have 2 junctions, and I actually have 4 currents. Out of the positive into the negative, so that, I'm going to call that I1. We'll call that I2, I3, and I4. And then now, give me a second, and I'll sketch this on my axes over here. Wait, hold on one second. Where? Here? Yeah, that's all I1, right? Because there's only one path. Yeah. I3, yeah, but remember, the current cannot go through junctions. So that's why at a junction, it's got to change. All right, so there's my circuit on my kind of 3D plot there. This is part of your Y for the test, folks. So you need to be able to do this. What does it say? What does the plot have to be? Look on the rubric you picked up yesterday. What did it say about the plot on that rubric? Usable. Usable. Close, Joe. Usable. Usable. So, let's see. This I know is all going to be up at 12. So, a bunch of lines up at the same height, hopefully. all of this section is all at 12. And then all of this section is something below 12, but not at 0. And then that final part is at 0. This part back here, I know is all at 0. I go up to 12 here, across, cross, down, cross, down, cross, down, 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 cross, 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 and down. And that would be my plot. And now I go through and label 12, 3.9 I1, 7.8 I2, 19.5 I3, 11.7 I4. And that would be a full credit Y. You guys need a minute to catch up? Okay. Let me know when you're ready, and if you are ready, start thinking about junction equations and loop equations and how many of each you have and things like that. Yep. If you look at the rubric, you'll notice what percentage each is worth. Do you have that rubric? Okay. How many junctions in the circuit? 2. So how many junction equations? Just 1, because that's the uniqueness, right? So the junction equation, I'm just going to start my how below this. That I would put, let's see, my junction, I'm going to do the bottom junction here. So into the junction I have I2 and I3 and I4 going into it, and then coming out of it I have I1. And what I'm going to do is grab that and then move it down below. I just wanted to be able to see it while I was doing this. That's the first of my equations. How many loops could I go through on this circuit? Now, who's working on this one with me so I know who to make eye contact with? More than that. More? More? 6. There are 6 loops. Now, that doesn't mean I need all 6 loops. There are 6 possible loops, because I can do 3 through the battery, taking each branch different time. And then I can do 3 just around the parallel section, big one around the outside, 1 around each side. So there's 6 altogether. But remember, what I need is enough equations to be able to solve for my 4 currents. To do that, how many equations do I need to find 4 unknowns? 4. But I got to make sure I have at least a junction in there, at least a loop, and that all the junction equations cover all the currents, all the loop equations cover all the currents. Really, yeah. So I could do, if I pick the correct 3 loops, I'm good. That's why a lot of times, if it's easy to do, I'll do all 6 just to cover me, so I don't have to figure out. So I'll do all 6, but realize you could probably get away with just 3 of them, like the 3 that go through the battery and through the 3 branches. You just want This covers all the currents, right? So I want to pick loops that also have all 4 currents in them by the group I picked. So I'm going to start writing the loops over here. I'm going to start in the bottom left corner here, bottom left corner, right here for these. I'm going to do 12 minus 7.8 I2 minus 3.9 I1 equals 0. And then I'll do 12 minus 19.5 I3 minus 3.9 I1 equals 0. I know I'm going a little fast. I just want to make sure you guys have a chance to try this one. And then 12 minus 11.7 I4 minus 3.9 I1 equals 0. Now, if I look at that stack of 4 equations, my red has all 4 currents in it. My 3 greens also have all 4 currents in it. My guess is I put those 4 into my solver, and I'm going to come out with a correct answer. I ran through the three big loops that are there. Those 3 that go around and come down through each of the independent branches. Now, the last 3 that I can do, and I'm going to do them just to show, are the 3 that just go around that parallel part. So they're ones like, sorry, I can't show both at once. I'm going to come down the 7.8, so minus 7.8 I2, then go back up through the center, so plus 19.5 I3 equals 0. That's kind of that left-hand loop. Then doing the right-hand loop, if I come down the center, I have negative 19.5 I3, and go back up the outside, give me 11.7 I4 equals 0. And then completely around the outside, minus 7.8 I2 plus 11.7 I4 equals 0. So those are my other 3. But notice, those 3 only have 3 of the currents in it, right? So if I picked the blue equation and the red equations, I probably would not come out with an answer, because there's not every current in the blue. I might, but I'm assured to come out with every answer if I pick all 7, or my guess is the red and the green. I'll do the red and the green to make sure I come out with an answer. Oh yeah, definitely. Not math class, so use your solvers. All right. In fact, I think for this class, I will use the gray solver, a 3rd solver. I'm just going to go and type into my computer. So, what letter do I employ there? And also IJK. They take those as unit vectors. So, I'm going to use ABCD. And I need to move this over so I can see these. So let's see, I have B plus C plus D equals A. Now that was my red one. And now I've got 12 minus 19.5 minus 7.8 B minus 3.9A equals 0. 12 minus 19.5 C minus 3.9A equals 0. 12 minus 11.7 D minus 3.9A equals 0. I'm going to tell the computer that I'm using A, B, C, and D. Cross my fingers. Yay! So it's telling me that I1 is 1.56 amps. Let's just check one of them right off the bat. Let's see. I1 is through that one, so that would be I1. What did I say? 1.56? 1.56. Chances are, if one's right, they're all right. So it did work, our strategy of only having to find those four. As long as you just got to cover all your currents. Picture? No, no pictures. Just toasting. Plus, your equations are going to be completely and utterly different because you have completely and utterly different numbers. There we go. Did it work for you? Excellent.